Boa tarde, good afternoon. Over the last 14 months, at the same time, we have experienced a situation that we never imagined. We also have witnessed extraordinary progress in science and technology. Good afternoon. Over the last 14 months, computing is an essential component of this evolution. And our students are those that should be capable of producing technology that will enable further progress in a sustainable manner. We are almost finishing our second semester here with remote classes due to the pandemic situation. Then Luciana and I thought that it would be a good time to invite Professor Jim Kurose, a distinguished researcher, to share his thoughts about the evolution of computing, what can it bring to our lives, and what is needed in computing research and education to keep it in the right path at the right pace. So it's a pleasure for us to have him here today. Thank you in advance for accepting our invitation. And I invite Luciano to introduce Professor Jim properly. Thank you.
Hello, everyone. Hello, Jim. It's our pleasure and honor to have Professor Jim Kurose with us today. I got to know Jim in person back in 2001 when he was a keynote speaker of the Brazilian Symposium on Computer Networks and Distributed Systems in Florianopolis. Back then, I was a student, and I remember other students and I chasing him for an autograph of his already best-selling textbook. So you can imagine how glad I am with the opportunity to have him here today. Let me try to summarize a few of Jim's accomplishments. Professor Jim Kurose is a distinguished university professor of computer science and associate chancellor for partnerships and innovation at the University of Massachusetts Amherst. From 2015 to 2019, Jim served as assistant director at the National Science Foundation, where he led the Directorate of Computer and Information Science and Engineering. In 2018, he served as the Assistant Director for Artificial Intelligence in the White House Office of Science and Technology Policy. During his career, Jim was recognized with numerous awards, including the prestigious IEEE INFOCOM Award, the ACM Sigcomm Lifetime Achievement Award, the ACM Sigcomm Test of Time Award, and the IEEE CS Taylor Booth Education Medal. He's a member of the National Academy of Engineering and a fellow of both the ACM and the IEEE. As I have many students here who are having classes with me this semester on computer networks, I have to say that Jim, together with Kate Ross, is the co-author of the textbook we are using, Computer Networking, a Top-Down Approach, now in its 8th edition. Jim, thank you very much for your generosity to speak to our community at INF-UFRGS and many colleagues in Brazil and abroad. So I pass the floor to you, Jim.
Great. So thank you very much. Thank you, Luciano and Carla. Thanks also to Lisandro. I'm really happy to be here. I'm not quite sure because of the arrangement for streaming exactly who's here, but I've visited Brazil many times at SBRC, but also to visit schools. And then actually when I was at the National Science Foundation in the United States, I was really happy to be able to start up a collaborative program in cybersecurity between Brazil and the United States. Also, I've traveled down a lot for that. So, sometimes travel's difficult, but I always love coming down to Brazil. So I'm really sorry I can't be down there. I've never been to actually as far south as Porto Alegre. I've been to Florianopolis. I've been to Rio, Sao Paulo, Búzios, Salvador, Brasilia, but I've never made it that far south. So I'm hoping I could come down sometime. But I'm really happy just to have a chance to sort of share some thoughts with everybody here about computer science a little bit more broadly than just computer networking. I think there are a couple of computer networking slides, and I couldn't resist putting them in, but really just some thoughts about where computer science is heading broadly. That's the title of the talk, From Artifacts to Systems to People. I wanted to let you know a little bit about just sort of what's happening in the United States in terms of, because I got involved with that when I was at the National Science Foundation and in the Office of Science and Technology Policy, sort of what's happening nationally from a US perspective in terms of computing, and then talk a little bit about education. So that's sort of, what we're doing here today. Those of you who know me or have heard me speak before, the worst thing is for me to just start talking and go on for, most of you are faculty, you don't want to just sort of drone on for 40 or 50 minutes. I could do that, but I don't want to. So I'll try to stop. I think we're taking questions. People are going to be typing in questions into whatever their streaming platform is, and then you're going to relay them to me. Is that right, Luciano?
Yes,
so I'll see them on the Zoom chat.
Yeah, we are reading the comments on the chat, the YouTube chat.
Oh, the YouTube chat. Okay,
people can just type their questions or comments, and we will try to summarize them from time to time during your talk. Okay, Jim?
Okay. So that sounds great. So let me share my screen, because of course I do have a PowerPoint presentation, and I sent a copy to Carla and Luciano, so if anybody wants the slides, they can just pick up a copy from them. And let me start a slideshow. Does that look okay?
Yes, perfect.
Okay, great. So again, this is the title of the talk, but generally it's mostly about reflections on computing, and in particular, where some things are heading. So, I want to start off, I'll tell, I love to tell stories, right? This was a poster I had on my bedroom wall when I was a kid. And I don't know, it was popular in the United States. It was after the Apollo landing, and you sort of see your place in the universe. And so, at my university, I've been a department chair, I've been a dean. Now I'm an associate chancellor. When I was, I think, probably a department chair, maybe a dean, I would talk to the head of the university, our chancellor, about how important computer science is to the university. And I remember once sitting on the other side of the table from him, telling him how important computer science is for a modern 21st century university. And his comment to me, listen politely, and says, Jim, everybody who sits in that chair thinks that they're the center of the universe. And I said, yeah, I can appreciate that. But in the case of computer science, it really is the case. So, I want to, a message I want to impart to everybody is that I think computing is just so important to everything, to so many things that are happening in the world, that are happening in our countries, to science and engineering, but beyond science and engineering, really to all parts of the university and all parts of social and civil engagement. And so that it's really an amazing time to be in computer science, right? That computing, to me, maybe it's just, everybody feels what they're working on and their community is at the center of things. But I think computing is everywhere. It's across all areas of science and engineering, all of society, that we're engaging. I think a theme you'll see in what I'm going to talk about today is that computer science is increasingly engaging with more communities, and that there's an urgency to our work. Okay, so this is what I'd like to talk about. I'd like to sort of think about the field as a whole. I know most of you are not computer networking people, so I have a couple of computer networking slides, maybe just one in there, but talking about the evolution of computing, just sort of the big picture historical view in my mind, from artifacts to systems to people, to talk about nationally some of the things going on here, and then to talk about education, because after all, we're all in universities, and education is important. So, I want to start with this notion of artifacts. So artifacts are things we build to systems to people. And I started in 1965 for no particular reason, except that that's when my Department of Computer Science was founded. And the artifacts of computing are the things that we build. the operating systems, the programming languages, networking, of course, the most important artifact, right? Databases, architecture, and some of the theoretical foundations behind those or below those artifacts. And I would say, the first 40 years, 30, 40 years of computer science research was primarily about these artifacts. So when I was in grad school, the hottest thing on the planet was operating systems at the time. It was before networks even really existed, right? But I think there was a lot of focus in the early days of computing about the artifacts that we build, how to build them so that they're efficient, that they're, that they're high performance. And I think the evolution since about, I'm going to say roughly the mid 1990s to, 2010 maybe, has been about then taking these artifacts and thinking about systems, and in particular systems and applications, and doing that at scale, right? So at global scale, so the internet, right? A global scale network. The issue of information search, the web came up, social media, data science started, probably, well, aspects of data science have been around for a long time, but data science is a field of study, 2005, 6, something like that. The data center, the rise of data centers, 2005, 6 timeframe, and applications. And so the field went from sort of these standalone artifacts that we build and study for many years to these systems at scale. And I want to say now, I really think, so if I was a grad student and had to do it all over again, where I see a lot of the most important challenges are now at the people side of things. So, information and misinformation. I'm not sure how closely you follow, things in the US, but I will just say the amount of misinformation that's around is just mind-boggling. And I never would have seen that 5 or 6 years ago that would happen, because of artifacts like the network and social media. But it's not just about information and misinformation. It's about human augmentation, how computation can now help people. I mean, amazing work sort of at the boundary between, neuroscience and cognitive science and AI, people embedding silicon and neural pathways in people's eyes and ears and brains. And then, sort of the more usual augmenting what people can do by, whether it's smart glass or whether, it's just working with with an AI system to help you in your job. That notion of taking what people can do and augmenting that by adding computation and information and data to that. Issues of privacy, how we now work at NSF, we coined this phrase that I love, the human technology frontier, the future of work, the human technology frontier. Computing for common good, I'll tell you, here in the United States, that's become, data science for common good, computing for common good's become a huge rallying cry. This is, sort of the tagline or the phrase that my department goes by, the College of Information and Computer Science, computing for the common good. In AI, those of you who work in AI know about fairness, accountability, transparency, the application of computing, smart and connected communities, ethics. So, I do now, when I step back, I see this pretty clear evolution from looking at the things we build and making them cheap and high performance, to making them scale, to putting them together, to now the applications and the people that use them. And so if you'll forgive me, just one networking slide. I do want to put up one computer networking slide. If you want to read more about computer networking, as Luciano mentioned, I could recommend a good book for you. But, if I think about before the 2000s, what were so this is, the network protocol stack here, right? So the physical bit layer all the way up to the applications like the web and TCP and IP protocols in the middle at the network and transport layer. That pre-2000, this is like a heat map. The dark red is where people in networking were really focusing, pre-2000 on the artifact and on performance, right? So at the transport layer, TCP, at the network layer, IP, multicast, quality of service, things like that. So there was a lot of focus on the artifact and the distinction between the edge and the core. I will say starting from about 2000 to 2010, the emphasis started moving up the stack to the applications, to the issue that folks are and users are mobile, to issues of security. And there's a story I like to tell. One of the best things about being a teacher is having grad students. And I remember I have a grad student, I'm not afraid to name him, Eric Nam. He works at IBM Research. So I knew him when he was, looking to come to graduate school and looking for a research group. And he came to me in 1995. So everybody in the field was sort of more thinking over here on the left-hand side. I don't know if you can see the cursor moving there. And Eric said to me, so Eric says, so what's your research project? And I said, we're doing this amazing stuff with multicast and TCP and, all this stuff sort of on the artifact inside the core. And Eric looked at me and he says, that's great, but the future is all in applications, right? And he was interested in real-time applications and multimedia and servers and things like that. He said to me, if you're interested in doing stuff in the core and on the artifact, I'm not interested in working with you because the future is moving up the stack. And so, here I was, I'm a full professor and this grad student's telling me I'm not working in the right area. But I really wanted to work with him because, you love students who challenge you. And so I said to him, okay, you're right. The future is applications. Let's work together. I'm not sure I really believed him, but I really wanted to work with him. And we worked on things at the edge and sort of up the stack. But he was 100% right. He, 5 years before, sort of saw this notion of everything moving up the stack. So again, in networking moving ahead, I would say from 2010 to 2020, the rise of data centers, again, mobility, security, privacy, even more emphasis on the application layer, how we manage, how we configure networks, and the people, right? So the privacy issues, the security issues, the quality of experience, as opposed to performance. And those are two different things. So the story in my own research area, sort of looking back on the 35 years I've been in networking, it's definitely followed this artifact systems, people, and things moving up the stack. Okay, so here's another view of this. This is from a colleague or a friend of mine at the University of Washington, Ed Lazowska, who talks about the foundations of computing, sort of the systems, the language, the architecture, what I talked about as artifacts sort of at the center. Then we have sort of the research areas. You might say, oh, I'm a wireless networking person. I do NLP, I do robotics, sort of those areas of computer science. But then again, on the outside, all of these application areas. And the way he characterizes it is a move from smaller, faster, and cheaper, so that's like artifacts, to tackling problems that are societal challenges that you see all the way out here. And so just another way of looking, and he and I sort of independently have been thinking about this and have been sharing slides, but I thought I'd show that to you. Okay, so the next slide I want to talk about, and I'm sorry, this is a little bit of a busy slide, but it has to go to the importance of computer science. And I wanted to show it to you because I was lucky enough, to work in Washington, D.C. for 5 years and to talk to folks in our Congress and our Senate and in the White House about the importance of computer science. And this is a picture, this is the picture that I always used over here on the right-hand side. This is what's called the tire tracks diagram. And so I wanted to, if nothing else, I hope the next time I'm down in Brazil and hopefully, get a chance to see many of you in person, that this might be one of the things you take away from this talk, this tire tracks diagram. You can see the reference to it on the left. And let me show you what it is. So what it is, well, there's a networking tire tracks, and then there's one for software technology. So on the y-axis, you see time, and you see 3 tire tracks, a red and a blue and a green. And the red is when research started in the university. So in the case of networking, the blue is when research started in industry. The green line is when this became a $1 billion product. or product and service area. And when it gets thicker, it's when it became $10 billion. And the most important thing here are not those lines or anything like that, but the arrows that go back and forth. And each arrow is a documented case of an artifact, something that got built, a piece of software, a piece of hardware, a paper, a person, an idea that has flowed back and forth between the university and industry, and then eventually translated itself into industry products and services. And to me, and so in my role in working at the National Science Foundation, this interplay between what happens in a university with federal funding, what happens in industry, and the economic impact of that is a very, very powerful story, especially when you're talking, to people in the White House or people in Congress or Senate about why they should be investing in computer science research, at a high level. It's this interplay again between industry, the university, and the translation into products. And this tire track diagram, I'm not going to go through this. This is in lots of different areas of computer science, so it's not just software and networking, but AI and architecture and parallel and distributed systems here. And again, I think at the end I've got some pointers to readings, but if you just Google search on tire tracks diagram computer science, you'll find this. Okay, I want to show you what the original tire tracks diagram looks like. So it's a little bit hard for you to see because I know it's small here. But you can see sort of the tire tracks, but they meant slightly different things here. You can see the areas, graphics, networking, workstations, the use of windowing as a user interface, risk architecture, VLSI design, very much focused sort of at the guts, the insides of computing. And so thinking about the artifacts that we built, right? Time sharing, graphics, again, networking, parallel computing. In 2020, so just last year, so this is way too small for you to see. I'll just show you what it is. It's the most recent version of the tire tracks. So you still see the areas. You've got communications, systems, theory, database, security, robotics on the far left-hand side. You have the IT innovations, again, the internet, secure computing, things like that. On the right-hand side, you still see these arrows going back and forth. But what they added this year are both the tech companies that have been spawned by that. So tech companies we all know, Qualcomm, Cisco, Broadcom, NVIDIA, IBM, Intel, Google, on and on here, and what segments they're involved in. So again, speaking to the industry impact, the economic impact of our research, and then finally, other sectors, and this is really getting to the people side of things. Agriculture on the right-hand side, automotive, e-commerce, health, entertainment, sports also. I wasn't really happy to see sports in there, but so be it. It's their report. But it talks again about from artifacts to systems, and then economic impact, and then finally people at the end. Okay, so I hope you sort of appreciate sort of that feel that even with these tire tracks diagrams that, again, I really like and use all the time. Again, this notion of moving from building things as computer scientists and computer science research, a focus, yes, we still have to build high performance things, but I would say the emphasis has shifted from artifacts to systems to people. And so let me pause there. So I've been going on for a bit here. I'm going to tell you a little bit about some things happening, here in the US in terms of the national imperative for computing. But let me unshare my screen, or unshare that just so that we can see each other. And if there are any comments or questions, we could try out the comment and question. I don't know, Carla, Luciano. Sorry. Whether there have been comments you could type into chat or questions you could type into chat.
Okay, yes, sure. Can you hear me? Yes.
I can hear you. Oh, sure, you can just say them to me, yeah.
Yeah, okay. We have a question from Sergio Gutierrez from Colombia.
Okay.
And his question is, if you could define a few orthogonal knowledge areas which drive development, which would be those areas? Orthogonal areas that drive development, which would be those areas?
Okay, so it's hard to now ask questions back, but you know, if you think about orthogonal areas that are driving, you know, orthogonal areas to computer science, I would say certainly anything having to do with mathematics and statistics in particular these days are certainly, you know, partnering institutions. And actually, if that's what the question was about, it's sort of a great segue into the next part, because I think there has already started, and so we started to try to promote this inside NSF, closer collaborations between the social sciences. So think about psychology, cognitive science, think about economics, anthropology, sort of the more people side of the social sciences, and computer science. I mean, for me, I just see such tremendous overlaps of research interests there. At UMass, we've started computational social science, public interest technology. So areas that sort of intersect policy, people, technology, where, you know, technology really means computing, that there's lots of really interesting things that can happen there. And I'll talk about that in a second.
Another question, Jim. Given this new, let's say, new moment where we shifted from artifacts to systems, and from systems to people, how should we as researchers in computer science, let's say, work? I mean, probably we're going to talk a bit more about that in the next part, but should we start from scratch? Since the beginning, I mean, exchanging ideas with people from other areas, or should we still stick to the computer science fundaments? How should we do? How should we behave as researchers in this very new, challenging moment?
Yeah. Well, first of all, there's no should, right? Because the nicest thing about being a researcher is you get to do what you want, right? And so, you know, I will say for myself, I've still, you know, I have a thread of research that's still sort of very much focused on the artifact, right? I was drawn into networking because, you know, the notion of how do you get something with, you know, billions of pieces of distributed interacting, you know, pieces together, and how do you manage that? To me, that's an intellectually deep question, and I'm still interested in that. So, okay, yeah, you know, everything I've said from artifacts to systems to people, I still think there's lots of really deep and interesting questions, you know, not just in networking, obviously, but in all those areas. So if that's what you enjoy, that's what you should do. What I'm saying is that I think now there's a whole new class of problems, sort of more on the application and use side, where I've also sort of personally decided to start spending more of my time. And so I'll give you an example. I have talked about this before, I think at UFRJ. You know, I was involved in a sensor nets project, which what a networking person would call a sensor nets project on collaborative adaptive sensing of the atmosphere. We called it CASA, right? And so I got to work with radar people who were designing the radar, you know, the waveforms, and then my group was responsible for working with the communications and the networking. But we also interfaced with the data people. We interfaced with the meteorologists who were running their algorithms on our infrastructure. We interfaced with social scientists who were trying to deliver warnings about hazardous weather based on what we were seeing. So it was very interdisciplinary and intellectually incredibly rewarding, right? And I was so thankful. And I worked on that project for almost 10 years. And it was intellectually deep and rich. So, you know, there's no should, it's what interests you. I think there are going to be maybe a message to take home is that certainly in the United States, there's going to be a lot more opportunities for funding, for example, that will try to promote this interdisciplinary collaboration. But it's a great question. So maybe one more and then I'll move on.
Yeah, sure. Carla, would you like to ask? I see we have a few more questions, but we pick one at least. We pick one and then move forward. Yeah.
Okay.
Yeah. So Cesar Marcondes said, in early ages of computer science, most of the innovation came from universities. It seems recently lots of research innovations are coming from companies.
Yeah.
What do you think about this shift?
So I'm going to both agree and disagree with that statement, right? Because I think, the nature of research, and so, I have lots of friends who are working in research labs and industry. Their research, again, is geared more towards what their company is doing. I mean, there's always exceptions to this, right? But I mean, if you think about, I shouldn't name companies, but I will, right? Think about Google, think about Microsoft, think about, Cisco, think about Qualcomm, right? I mean, they all have their core business and their research is geared towards what their business needs to do. There are certainly people in some of those companies who tend to be, some reason they're able to work on whatever they want and it might have very little application. I still think the longer term research and the more fundamental research is happening in universities. And as you'll see, so it's a great question. I actually, and one of the things I tried to promote, I think I took the slide out of the deck because it was too NSF specific, but collaborative research projects between industry and academia, where NSF would provide funding for the academic researchers. We did 6 joint calls between the National Science Foundation and Intel, for example, on aspects that, they're fundamentally important aspects. Intel says, oh, we think there should be more research in this area, whether it's, named data networking at the wireless edge or something on security and privacy in wireless communication. We did a bunch of calls with VMware having to do with security and sort of a cloud environment. We've done things with Amazon on fairness in AI, right? Fairness and ethics in AI systems. And so, that's not geared towards I shouldn't make any comments about product lines, but those are fundamental research questions. I think when industry and universities can work together, wonderful things can happen. So, okay, so let me, and thank you for the questions, and queue more up. And if we don't get a chance to go through all of them, I'd be happy to continue conversations online with people.
Just to provide you a feedback, Jim, we have now 150 people attending your talk.
Oh, well, great. It's a little bit too bad I can't see who folks are, but I imagine I know some of you and have met some of you out there. And so I just should say hi. And for those of you who I don't know, I hope to get to meet you all in person, at an SBRC or something like that at some point in the near future, once we get past this terrible pandemic. Okay, so the next part of the talk I wanted to talk about is actually perfectly aligned with a couple of the questions that came up about collaborations with other disciplines. So this is a word that I hadn't heard until I went to NSF, and you might want to read about this some. It's called Convergence Research. And when I was at NSF, so I led computer science, but my boss was the overall boss at NSF, and she kept talking about convergence research. And I said, it just sounds to me like another word for interdisciplinary research, because that's partially what it is, right? So, so it's about working across disciplines. But what I learned, she told me, you have to stop saying that because I've answered your question 10 times and you keep asking me. So it took me a while to internalize what this meant, but it's about solving big problems. So it is interdisciplinary research, but it's interdisciplinary research that's driven by a very specific and a very compelling big problem. And it requires sort of intentional integration across disciplines to solve it. So that's what convergence research is about. You see National Academy of Science Studies, you see our engineering research centers talking about it, you see MIT, talking about it. At NSF, we started something called Convergence Accelerators, which were really sort of aimed and completely at this. So this notion of convergence research is something that has a lot of currency, if you will, in the United States. I think in terms of collaborations, and I've talked about this already, so I won't say more, except to say that it is, I think, we'll see a lot more collaboration between computer scientists, social scientists, cognitive scientists. In the US, that NSF, that's social, behavioral, and economic sciences, SBE. You can see this is a letter on the left-hand side that I wrote with Faye Cook. She was leading, she's a social scientist. She was leading the Directorate of Social, Behavioral, and Economic Scientists. This is something that we wrote in 2017 to our community saying, hey, look, we're really looking, it's important to collaborate here, and we started new programs in that. You see a program solicitation that just was released maybe a month ago on the future of work at the human technology frontier. It's a joint collaboration between social behavior and economic sciences, computer science, engineering, and education. So those 4 directorates. So, when folks in my university say, what do I think is going to be a hot area, or especially intersection area, I think computer science and social, behavioral, and economic sciences, in the States anyway, is going to be an incredibly important area. So I don't want to talk too much about bills and things like that, but I will say that the Congress and the White House, I've just got a few slides here just to show you where things are going. There's an increasing focus on university researchers getting together on center scale, use-inspired research. So there was a bill sort of authorizing that. This is, if you're an AI researcher and you haven't seen this, or even you're interested in AI research, just Google the title there that you see, search for the title that you see there, a 20-year community roadmap for AI research in the US. This was put out probably about a year ago now, and it calls for mission-driven AI laboratories that are funded at $100 million US per year, but also is very detailed in terms of areas of artificial intelligence that need more investment. And so for me, that was a very important document. That document was important to the National Science Foundation in making the case for increased funding in AI. We also have what are now called AI institutes. The first set of 5 or 6 were launched last year. Another round would be launched this year by the National Science Foundation. These are order $20 million for each institute over 5 years. Okay, so in addition to the collaboration between disciplines, doing so in the context of convergent research and sort of at center scale, picking a big problem and going after a big problem. So Luciano mentioned that I've been at the National Science Foundation. I'm not anymore. I still have a lot of friends who work there. And while I was at NSF, the budgets went up 2% a year. I mean, a 2% increase is better than a cut, right? And I know, lots of countries are struggling with cuts in their scientific research budget. But the whole time I was at NSF, the budget went up 2% a year. The budget proposals that I'm going to show you here have NSF's budget, research budget, increasing by billions of dollars a year, 10, 20, 30% in 1 year. So these are the kinds of investments that the US Congress, the legislature, our Senate, and the president are all pushing for, and all within the last 1 or 2 months. So I just thought I'd give you a heads up here. From our Congress, from the House side of our Congress, there's something called the National Science Foundation for the Future Act that came out a month and a half ago that proposes a new science and engineering solutions directorate. So this is, again, that use-inspired type of research, and to put another $1 billion in it starting next year, and to increase NSF's budget by $3 billion. And so this is about a 40 to 50%, close to 50% increase in the NSF in the space of just 1 year. Sorry, it's $3 billion total, so 30% increase in the space of just 1 year. So that's a really significant investment. In the Senate, there's something called the Endless Frontiers Act that was just introduced 2 weeks ago. It again calls for a new directorate in technology and innovation. So you can see this notion of computer science driving economic competitiveness. NSF, the current budget is $8.5 billion a year. This calls for increasing the budget, putting $100 billion over 5 years, so averaging $25 billion a year into an agency that's only $8 billion, $9 billion right now. And you can see strengthening the leadership in critical technologies through basic research, focused on commercialization. So again, the question asked earlier about universities and industry collaborating in key technology areas and also on education. And then finally, well, actually, I should show you a little more details here. Just look at the areas on the side, right? So this is the endless frontiers coming from our Senate. These were the 10 areas across all of science and engineering that were identified here for investment. AI and machine learning, high performance computing, quantum and information systems, robotics. So I'm not talking about computer science. This is across all of NSF where they say this is where the investment needs to be. You know, computing is really central here, right? So remember that first picture I showed where with computing being at the center of the universe, you know, this is, maybe I'll introduce this as evidence for that. But also disaster prevention, communications, wireless, you know, internet technologies, biotechnology, security, advanced energy, material science. So these are the 10 areas identified in the Endless Frontiers Act that would get a lion's share of that kind of investment. It doesn't go into details about what the individual budgets would be. And then finally, our president every year, so this came out just 3 weeks ago, I guess, the president says, again, create a new NSF research directorate to translate research into practical applications. So again, from artifacts to systems to people, and doing things that impact people and the applications that impact people. And the White House's proposed increase is $1.7 billion, again, for an $8.5 billion agency. So 25 or 25% increase in a year. So I felt like I left NSF at just the wrong time, right? Just before this very much needed investment happens to expedite technology development in areas that are crucial for leadership. And you can see the areas listed: AI, high performance computing, disaster response, quantum, communication, robotics, you know, a lot of areas in computing. Okay, you might ask yourself, why is this happening? I'll just put this out here. You can infer what you want. This is what's showing here is the amount of, on the left-hand side, this is the total amount of GDP, gross domestic product expenditures on research and development. And you can see the US is the top curve there. That curve that's going up really fast is China. The curve that's going up at about the same rate as the US is the EU. And to come to the question about what's happening in industry versus what's happening in academia, take a look at that slide on the right-hand side. And what that does is that breaks out where the source of funding for these research and development, so I will say and expenditures are. And you can see business is that top purple curve. The federal government, and so, you know, NSF in computer science funds 87% of all US federal basic research in computer science. So if you're thinking computer science piece of that, you know, that red curve is really, you know, NSF is most of the federal government there for basic research in computer science. You know, you can see that's pretty flat. So the comment was more is happening in industry. Well, I will say it's absolutely true. More is happening certainly from an investment side, and that curve shows exactly that comment that was made earlier. Okay, so I want to we'll take a break for a few more questions in just a second. I want to show you one other actually slide. Actually, I'm quite proud of the animations on the slide, but that's not really what I want to show you. I want to show you a way of sort of thinking about research that I've found really useful. There's a book that came out, I don't know, 20 years ago called Pasteurs Quadrant. And what this book says is that think about the x-axis here, how we use our research. You know, is our research purely curiosity driven, right? So you just want to work on it because you just want to work on it and you're not quite sure how it would ever be used, right? As opposed to at the far right-hand side of the x-axis, use-inspired research, right? So that's one axis. Another axis is, whether your work is super applied or whether it's fundamental. So this is the, the four pieces of the space that Stokes, the author of this book, so highly recommend the book to you, laid out. Okay, so fundamental research, right? So think of Niels Bohr, think of Madame Curie, right? That they didn't really know, Bohr discovers the atom, Curie's looking at radiation. They don't know how it's going to be used. They're just doing basic research. Over in this bottom right-hand corner, Thomas Edison, inventor of the light bulb, George Washington Carver, a lot of agricultural research. They were really inventors. You might not call them researchers, you'd call them inventors. They wanted to do something because next year they would have a product. Edison found it, you could trace it to Bell Lab, founding of Bell Labs, right? That they're really inventors. And then up here in this quadrant is, where you have the use-inspired basic research. And I would say a lot of computer science sort of falls in there. And so Louis Pasteur, the French researcher, is someone whose research falls there, right? So Pasteur, we're all worried and we're thinking about vaccinations now, right? I mean, Pasteur was working on vaccination in animals to prevent disease spread in animals. Pasteur, in English, we say pasteurization of milk. I don't know if there's an equivalent word in Portuguese, but that was phenomenally important for with milk, for example, in the United States, pasteurized milk and stopping the spread of disease and childhood diseases through pasteurization, what became called pasteurization. So the National Science Foundation would say, oh, you know what? We fund both basic and pure research, and we fund the use-inspired research. And I've been talking more about the use-inspired research. But I want to show you now another way of looking at this axis, and actually another axis, a translation axis. So translation means taking your research and doing something with it in practice, translating it into economics, or translating it into practice. And so here's the animation I'm really proud of. If you make PowerPoint, I want you to take a look at this, right? So what I want to do now is I want to look at this axis of pure versus use-inspired basic research and look at translation, right? And so think about taking that cube and sort of rotating it. I don't know, it probably didn't rotate smooth for you, that's okay. The idea here is to talk about curiosity-driven and use-inspired research. Think about that tire tracks diagram. Think about taking research and the impact that it makes. And think about that impact axis on translation as being, some kind of time scale. So if you look at what's happening in 3D printing, some of the technologies behind the iPhone, what's happening in deep learning, right? You can trace back the research that has driven those innovations in services or products back to research that was done 30, 40 years ago, right? And curiosity-driven research, quite honestly. When people weren't worrying about neural networks, nobody said, oh, I'm building a neural network so I can train it so that I could do, stop sign recognition in an automobile, something like that. They weren't talking about that in the 1970s and 80s or the 50s when some of the early neural network work happened. It was all curiosity-driven. There is more use-inspired research, right? So Akamai, which does content distribution, we know what Google does. I mean, both of those companies were founded out of NSF-funded research, but that were in a particular, area. So Hector Garcia Molina, who was at Stanford, had a grant in digital libraries, and I remember reading his first annual report. So this was, he did this in circa 2000, saying, we're being funded in, sort of this digital libraries project. We've started addressing this question of how do we search for things on the internet. We've decided to start a company that will do search, and we were calling it Google, right? So that came out of their first annual report, which was pretty amazing. But so there is this notion, both on the curiosity-driven side and the use-inspired side, of taking that research and translating it into practice. And that's what you're seeing in those earlier pieces of legislation in the United States, specifically funding research that's sort of, I think, more happening here. It's a little bit more use-inspired, where the timescale of translation may a little bit be shorter. I should say, those proposals for all of that funding raise everybody's boat, right? All boats are floating, right? So fundamental curiosity-driven research is being funded at higher levels. So is use-inspired. Probably use-inspired, the increments would be a little bit higher. I'm just guessing. Okay, so that's all I wanted to say on that. And I was going to say a word about partnerships with industry. I've already talked about that a little bit. I talked about the Intel, the VMware, Amazon, some of the, we've also been NSF has been partnering on a $100 million wireless testbed power that some of you in networking probably know about. So I'm not going to say anything more here. There's more reading. I have lots of homework. If you want to do homework, there's plenty of homework to do. So let me stop there. I want to just say a few closing words about education in a second, but maybe I'll stop there and just see if there are more questions or comments.
Okay, Jim, there is a question by Sergio Bumpy. He's a colleague of ours. He's from microelectronics area, and he asks, VLSI chips, WDM, integrated lasers, better fibers. Yep. Without harder advances, none of that would have happened. What do you say about the cost of these artifacts worldwide? This is one question by him, and I will connect to the next question by André Reis, who is also from UFRGS. Considering it is difficult to obtain funding, is it possible to achieve worldwide relevance while working on tight cooperation with the interests of local mid-sized companies and startups? Can we be local and global at the same time with a small budget, or research is only possible in our area with large budgets?
Yeah. Okay. So those are all great questions. Let me start with the first one, which was about development of specific technologies, right? And so, for those technologies, the early research in those areas, absolutely, I think, you could trace a lot of that coming out from academia. I think as the technologies have become more and more advanced, let's only take computer architecture. And again, this is just my personal opinion, right? So as computer architecture has become more and more advanced, and okay, so now we're down at 7 and 5 nanometer technologies for doing fabrication. You can't do that in a university, right? So there are certain things that if you want to do them, that are, I think, very technology and also very, intensive if you want to work on, whatever is beyond 5 nanometer, 7 nanometer technology lithography for doing chips. You have to do that in industry. You just can't do that. There's just not the capability of doing that. I will say that I think that that kind of research you have to do in industry, that it tends to be a little bit shorter term in the sense that the specific goal, the next generation of scaled down technology is going to, it's going to come out in 3 years or 5 years. So the timescales are a little bit shorter. There's nothing wrong with that, right? I'm just saying that as a fact. One of the things that we're seeing happening a little bit more in the AI space than in the technology space is universities starting to develop relationships where faculty actually have appointments in both sides, right? Because we have a shortage of faculty, especially in AI, at least in the United States. And so you'll find that people have a half-time appointment in a university and a full-time appointment, or a half-time appointment in industry, and they'll move back and forth. And sometimes it might be, 80%. I was just talking to someone who was almost 100% in industry, and now they're almost 100% back at their university, but they've had a foot in both along the way. So that's one way to do collaboration. I want to address the question which is just superb, about scale and do you have to do it big? And the answer is you don't have to do it big, right? You have to choose the research, I think, and this is just me, right? You have to choose the research problem that fits the environment in which you're able, and you know, the connections you have and the people you're able to work with, right? And so to me, that means, you know, I don't, it might seem otherwise because I've worked at NSF and things like that, but you know, my research is tied into, you know, people who are working, you know, sort of, you know, down in the trenches at companies. Some are big, some are small, and they have very specific research problems that they want to look at. You know, something that we'd write a paper on and publish in INFOCOM or Sigcomm, right? It's not going to be, you know, somehow I lack the entrepreneurial spirit. It's never going to build $1 billion industry or anything like that. But you know, it's meaningful to me, and you can collaborate with people in industry on those sort of small scale things. I mean, if you look at the papers I've written with folks in industry, we've always picked a pretty narrow problem and looked at a pretty, you know, narrow problem and wanted to work on the kind of research that you publish in Sigcomm or INFOCOM. You know, my kids ask me, why didn't I make a huge amount of money so we'd be rich? But you know, you do what you want as a faculty member, right? So maybe one more question and then we'll wrap up with education. Just a few slides I want to show you.
It's from Ricardo Reis, also from URGS. Power consumption due to computing device has a fantastic increase each year.
Yeah.
An estimation says that by 2040, all energy produced in the world will not be enough to run all computing devices.
Yeah.
What should be done to cope with that?
Yeah. So that's a great question. I would say that's a great area to be working in, you know, in terms of power efficient computing. But it doesn't just come down to doing it at the, you know, if you're sort of an operating systems level person, you might think about smart scheduling and, you know, the way most you think about computing, you know, there's a startup cost, and then as you start to scale the amount of communication, computation, the energy consumption goes up, right? So the real question is what's on, what's off, right? And so you can think about smart scheduling things for that. I want to say also that it's not clear to me, or maybe that as the field progresses, the amount of computation that you need to solve a problem will go down. And let me give you an example of that. There's a great graphic. I don't have it with me, but if somebody wants it, I've got it and I can email it, that looks at the amount of, so it was looking at something like, so it's an AI, it's a slide, it's by OpenAI, it's a graph. So on the x-axis is time, on the y-axis is the number of think of flops, you know, think amount of computation that's needed and for a lot of different AI machine learning systems. And what you see is, and this is a logarithmic axis, right? So a straight line is exponential increase, right? So what they plotted was the amount of time that's needed for each of these systems, the amount of computing time. And it looks like Moore's law, right? So it's a straight line, right? So it looks like it is an exponential increase in the amount of computation. So that's because of the statement about there won't be enough computation around by 2040, right? At the current rate, right, that you see the amount of computation, it was doubling, not every 1.8 years like Moore's law, but like every 8 months, right? And so the amount of computation needed is going up exponentially fast with a doubling factor of like 8 months, something ridiculously short. So you look at that and you say, okay, we can't go on like that forever, right? And so to me, that says, for instance, if you think about training deep neural networks, you might think about alternate ways of training them than just throwing massive amounts of data at it, right? So you might think about, you know, within AI, a lot of people are thinking about model-based training where you use models of the physical world to initialize, for example, how you're going to, you know, where you're going to start your training points, or you interleave those two so that you use something that's model-based along with something that's more data-oriented, and you can decrease the amount of computation. So that's just to say, there's a lot that the question of the amount of power and the amount of resources is a really important question. There are questions sort of down at the microelectronics center level. There are questions sort of at the systems level about how turn things on and off, how to schedule things, where where power is available. And then there are things at the algorithmic and sort of, within your application area, how can you think of techniques that require less raw computation and might be more model-based, which tend to require a lot less computation. But great question, great area.
Thank you.
Okay, so one of the things I learned is never to overstay your welcome. And so I'm going to take another 5. I just want to say a few things about education, and then I'm very happy to stay on and chat as long as people would like to chat. But let me just wrap up here with just a couple more slides. Let me share my screen. Share. Come back here and talk about education. Okay. So the first thing I want, so we're all computer scientists, mostly computer scientists here. Many of you are in universities. So if you want a slide to take to your dean or your university president to say, hey, you need to invest more in computer science, I found this was a pretty popular slide here in the United States, and I've certainly used it. So what this does, this comes from a part of the U.S. government called the Bureau of Labor Statistics that studies labor. And what they're looking at is they're looking at where are the jobs going to be from 2018 to 2008. So over those 10 years, where across all of STEM, science, technology, engineering, mathematics, where are those new jobs going to be? And so you see the big blue thing is in computing. You see the gray one is 21.8%. Are in engineering disciplines, mathematics 3%, physical and life sciences together 10%. So, I think it is fair to say that if you think about, one of our roles as educators is helping to educate a workforce for the 21st century, that this is where the workforce is going to need to be. And so, you could tell your dean that I said, I think it's really important that we invest in computer science education. I want to say one word just about computer science education and how it too is broadening, again, along these lines of artifacts to systems to people. Many of you may have heard of something called CS plus X. I don't particularly like that, but because it puts computer science first, and believe it or not, even though I think computer science is the center of the universe, you never tell anybody you're the center of the universe, right? Unless you're trying to make the case for them to give you some resources. So I like X plus CS, or in my university, we just call it informatics. But the idea is that in computer science, I'm sure your department, like my department, has an undergraduate program that looks pretty much the same way it looked 20 or 30 years ago, right? You've got introduction to programming and data structures and algorithms and networks and compilers and AI and maybe a machine learning course now. But this is the deeply technical material that we teach in our courses, right? And there are, certainly this is true in the United States. It's one of the reasons why my Department of Computer Science is now the College of Information and Computer Science, CICS, is because on our campus, there was a group of students who needed computing, right? That wanted to use computing deeply in application areas, but their goal was not to go work for Microsoft or Google or Amazon and work on their computing systems. Their goal was to take computing and to use computing in an application area. And that's called sort of broadly CS plus X, where X is any number of disciplines. So at the University of Illinois, for example, their CS plus X program, X could be law, X could be medicine, X could be physics, X could be music, X could be agriculture, right? And they have joint programs. I think they have 11 now, maybe it's eight or 11 programs, undergraduate majors that you could do in computer science plus X, where, X1 through X9 in that case. And actually this diagram I took from Rod Rutenbar, who used to be the chair of computer science at the University of Illinois. So you see law, health medicine, humanities, art, social sciences, societal applications. They're big in agriculture there. And we as computer scientists need to ask ourselves, what do we need to teach these students and how should we teach them who are not destined for careers that are deeply technical computer science careers, but a little bit more on the, they're going to use computing a lot in their application areas. And so you see a little quote from Steve Jobs there, but again, I think the idea is computing is central to what they want to do, but it's not our traditional curriculum. So we in Amherst, we have a new informatics curriculum that's a little bit more applications oriented and is structured differently. So, I should say that having a diverse workforce is something really important. I think this will be my last slide, and then I'll skip ahead. I'm pretty much done. One of the things that I was very proud of working on at NSF was this computer science for all. And the idea was to really try to diversify and broaden the pipeline of students who are coming into computer science. And one of the things that we did in the US, when you're graduating from high school, one of the things you could do is you could take an exam, like a national exam, not really for admissions into, there's a different exam for that for universities, but what's called an advanced placement exam, so that you show that in high school, so when you're 16, 17, that you've taken material that is equivalent to a university level first or second course in an area. So we have one, we've always had one in computer science. It's basically Introduction to Programming. So I told you about this deeply technical major versus informatics, or CS+X. Starting in around 2010, we started activities in the US. I got involved in this long before I went to NSF, about trying to create high school curricula for students that was more applications oriented, that would not be so programming focused on the creative use and application of computing, that would still teach fundamentals, teach a little bit of programming, teach what is sometimes called computational thinking, right? Or algorithmic thinking, or how to think about how to computationally solve problems. So there was a new exam that was introduced in 2017, a new computer science advanced placement exam that was introduced in 2017. It took 5 years of work to sort of, and a lot of it funded by the National Science Foundation, to get that exam in place. It's been offered since 2017. And since the graphs are a little bit low or small, you can't really see them here, I'm sure. But the graph on the left shows the total number of women who are taking one of these two computer science exams. And you can see the bump, you can see that tremendous, much more than you would have expected increase in the computer science AP exam by women on the left-hand side. On the right-hand side, you see a similar, very dramatic increase in the total number of students who are coming from underrepresented racial and ethnic groups in the United States. And so that doesn't count Asians, like me, for example, right? Because we're not underrepresented in computer science. And so there has been this effort to broaden the pipeline of students coming in to our universities to study computing. This computer science principles has been a really important thing, and a really important part of that. I think again, it ties in once again to this notion of artifacts to systems to people, because it does tend to be a little bit more applications oriented. Okay, so I have a few more slides. I'm not going to show them here. You could get a copy of the slides from Luciano or Carla, because I've sent them down. It was a little bit more about teaching and teaching online. I'm giving another talk tomorrow at UFRJ on sort of the online teaching of things, which is something I've been working on a lot recently, actually with Edmundo at UFRJ and also at my university here. Let me just finish up here by saying again, coming back to this message that I don't know about you, but I don't know if you've seen that movie Forrest Gump, where, you know, he sort of tends to show up at the right place at the right time simply by luck. And I feel incredibly personally lucky that, you know, some of you who are a little bit older, we got interested in computing before it was almost on anybody's radar screen, right? But it's turned out to be a field with tremendous importance. It's ubiquity, it's everywhere. The ability to engage in all these different communities, I think especially now, you know, with this interdisciplinary convergence collaborations, and then of course, all things about computing playing such an important role in what's going on in society. So with that, I'm sure I did overstay my welcome. I'm sorry. I apologize for that. But I thank you for all the great questions. I'm willing to. I can absolutely hang around. We can have more discussion. I can't see people leaving or anything like that anyway. But hang around if you're interested and you got a little bit of time. Maybe we could talk for another 10 minutes with questions and things.
I'm sorry. The virtual room is still full.
Okay, great.
Yeah, we have a lot of questions.
Okay, great.
I will pick one if you allow me, Carla. Actually, two students, Lucas Nobri and I don't remember.
Carini?
Andrea Carini. Can you go, Carla? Can you do the question because I can't see the chat from here? Sorry.
Yes. Okay, so Andrea Carini and also Lucas Nobri, they ask, what can you tell us about keeping undergraduate researchers to stay motivated on research, of course?
Okay, so first of all, hi Lucas and Andrea. So that's a great question. I mean, it goes to the motivation though of why you do anything, right, in life, or golly, that sounds a little bit too big, but so for I'll speak for me personally. I did research while I was an undergraduate in physics. I wasn't, my university didn't even have computer science when I was doing it, but I was interested because I think I was inherently driven I was curiosity driven at the time. I think as I became a graduate student, moved a little bit more into computing, I thought about the application of computing and what it did for people. So, very much this, artifacts, the systems to people, and networking and communications just played a really incredible role there. So I would say half of my motivation was sort of, maybe we could work on things that people would actually use, right? And that's exciting. And then to me, the other half was simply, I think I said this before, somehow just the intellectual curiosity about, for networking, how do you get billions of things to collaborate and do things in scalable ways was just an interesting question for me. And how do you stay motivated as an undergrad, or let me say as a graduate student? So, I would say my graduate and undergraduate interest in my research probably, it goes up and down, right? I mean, we all have good days and we have bad days, and you have time when you think like, oh my God, my research is absolutely going to rock the world. And then you have other days where you think your research is going to, is it ever going to come to anything, and who's going to care about my research? So first of all, if you have those ups and downs, I will tell you, I've never met anybody who doesn't have those ups and downs. In terms of being motivated, I always just think then about the big picture. I used to talk a lot with my advisor and would encourage my students to talk to me, So if you're feeling down about your research, your advisor's gone through the same things, or a graduate student you're working with, or one of your friends is absolutely going through the same thing, or has been. And so talking with other people, I think, helps that a lot.
Okay, thank you. Luciano, do you want me to go ahead, or
you can, please go ahead, Carla.
Okay, so I'll make a small change in order because of one of your slides. So Yuri Jacek asks, many reports say at least 1 million jobs will be lost with the fast booming of self-driving vehicles, particularly trucks. How do you balance that with a passion for technology advancements?
Yeah.
And
Yeah.
yeah, okay. The other question I'll read later.
Yeah. So that's a question I've thought a lot about, and again, this is just sort of my own personal take on this. It's for 150 years plus, well, since the Industrial Revolution, 150 years plus, this issue of automation taking, or well, let's just say it, taking human jobs away, absolutely happens, right? There's no question about that, right? It's also been true historically that new jobs have been created as well, right? And so let me give you an example that I found sort of struck really close to home was, I don't know if you've seen the movie, what is it? It's about a group of women who were working at NASA doing calculations for for the early space program, right? And they were doing calculations by hand. They were absolutely brilliant mathematicians. They were all mostly women. And it was about the time when, well, they did amazing calculations that sort of made the whole space program possible, but it happens at a time when computing is just on the horizon, right? And so what happened was their job as human computers, was taken away, but the whole field of programming sort of happened. And so I think that new technologies that come and make some jobs go away, make other jobs possible. Here's an interesting statistic I heard. It's from about 2000, I think it was about 2008. This was a study that I'm not sure I could find it again, but I'm telling you what I remember about it. It looked at children who were born in the year 2000 and said, by the time they get to be 35, what fraction of them will be working in jobs that even have a title now, right? And the prediction was 65% of the jobs that people were going to work in. And, it's just somebody's prediction, right? But they worked in a university, so I at least think it's interesting, right? They were claiming something like 65% of those kids who were born when they got to 35, the job that they had, that they would have, had not even been invented in 2035. And so, again, it comes to some jobs are going to be lost. It tends to be the more manual ones. It tends to be sometimes some of the more dangerous ones, and it gets replaced by technology. There's a long history of doing that. There's a long history of new jobs being created. There's a long history of education, therefore, being really important. And you can never say, the future is going to look like the past, but I don't think it's all doom and gloom. And, if it's not obvious, I tend to be a pretty optimistic person. So I do think there's optimism that there will be new jobs that come along to replace those old jobs. It's 100% clear to me that for those new jobs, education is going to be really important. Being able to work with computing, to work at that human technology frontier is going to be really important. Just think about, people who work in Amazon and work in their warehouses, right? What warehouse jobs used to look like 15 years ago, 100% manual, to now collaborating with robots at the same time. I mean, that's another example of, probably a kind of job that didn't exist even 5 or 10 years ago.
Okay. There is another question here. Martin K. I want to know, how would you evaluate the impact of COVID and this global quarantine in technology development? Maybe a faster shift to technology-driven for people? What do you think? Yeah,
so a couple of comments there. First of all, thinking about the vaccines, right? The messenger RNA. So there's now a whole new class of vaccines based on messenger RNA. The very first ones that came out, the Pfizer and the and the other one. The notion that I'm making a general pitch about research here, right? The notion that you could go from the genomic sequencing of the virus to the basic structure of how vaccines are going to work in the space of just a few months is amazing, right? And that's a pretty, people have said, could you imagine if this virus had hit 20 years ago, where we might be, right? Or how much worse it would have been, right? You're comparing it to the, there's a big influenza pandemic in 1918, where, people barely knew about viruses at the time, and how devastating that would be. So the first thing I want to say is that I think that research, as devastating as this pandemic has been, right? And I have lots of friends in Brazil I've talked to about how bad it is there, and it's been really bad here, and it's just horrendous in India now. As bad as it's been, it could have been worse, and probably would have been worse if not for the research, I think, that has happened. And I'll say again, research, the foundations of which, that kind of basic research is generally funded by governments. In the case of the US, a lot of that's at the National Institutes of Health, right? And so basic research plays a critical role there. I'll tell you that one of the things that I really appreciate, so I'll tell you, I was chatting with Luciano and Carla about this before we started here. One of the, if you can say a good thing that has come out of COVID is that we've now become much more used. It won't be the norm, right? I really do hope that I can come down to Porto Alegre and meet you all. I love to travel, right? I absolutely love to travel, but this wouldn't have been possible without Zoom, right? Honestly, without Zoom. I'll tell you, I love to tell stories. So another story I was telling them. Some of you may know there's something called the networkingchannel.eu. And if Edmundo's online, I'll plug him because he's going to be one of the 4 panelists tomorrow. So this is, just go to networkingchannel, one word, .eu. And so what we did was, a group of networking people just said, hey, look, our communities, we want to hold our community together. Why don't we just have once every 2 weeks seminars or discussions or panels or something like that. And, the whole world can attend, right? So tomorrow on the networkingchannel.eu, there's the panel is on how to be a good graduate student, right? And it's all networking and systems people. So it's Edmund from UFRJ, it's Randy Katz at Berkeley, it's Jennifer Rexford at Princeton, and it's Anja Feldman at Stuttgart in Germany, right? And there are more than 700 people signed up for that, right? So it's just virtual, 700 people showing up from every continent except Antarctica. Actually, I haven't checked for Antarctica. I did, so I know Luciano was on the first one that we did where we had Nick McEwen talk about software-defined networking. I sort of organized that. So we had Nick give a 20-minute presentation on that. Then we had a graduate student from Pakistan, from China, from Brazil, from the US, and I'm forgetting one country, Spain, and we gave them Nick's slides ahead of time and they engaged them in a conversation, then we opened it up for questions. We had 500 people register for that. That would not have happened in a pre-COVID time. So I do think using technology to build communities is maybe one of the good things that might have come out of this, and possibly the use of technology in education as well. And I actually believe that will be a good outcome also.
Okay.
Jim, many people are congratulating you and thank you for the enlightening talk.
Okay.
Many are commenting, and I have a final question for you. How will classes look like after this pandemic?
So I'm going to talk about that tomorrow in the talk that I'm going to give at UFRJ. Let me just tell you. So one of my jobs at the University of Massachusetts, I'm leading a university-wide task force on what we call flexible learning. And what flexible learning is about is it's about taking what we do on campus, so taking our on-campus courses and making them available off campus at the same time. It's more than that, but that's certainly a key aspect of that. And I've been involved in teaching that way for 15 years. I haven't done it in 10 years. Of course, I taught completely online this past year, but before that, it was just in person, right? And so I do think this notion of sometimes people call it blended classes or high flex classes or hybrid classes, but this notion that you could be a student, even a student on campus and not always show up for class, or you could be a student, who's on the UMass campus, but they're doing an internship. So they go, I live in a small town of 20,000 people, right? So there's nothing going on here, right? You want a job in computing, you go to Boston, you go to, San Francisco or San Jose, you go somewhere else. And so students do their internships, not where they go to college, right? They have to travel. But now they could be living in San Jose and still take courses synchronously, live with their UMass. So I could teach my computer networks course and I could have 50 students or 100 students on campus, but I could have 10 or 15 students off campus at the same time. I mean, that's something that, it enables richer experiences for the undergrads. It allows students to actually go off campus and do internships, to travel internationally, and at the same time still be able to take, not lose ground in terms of the classes that they're taking. So, in terms of education, I was never a believer in MOOCs as revolutionizing education. I think that, place-based education is a wonderful thing to have. If you can't get that, I think we're going to do better and better with online learning, right? And not everybody can make it, right? Your federal universities you've got an amazing system of federal universities in Brazil, but they're not everywhere, right? Not everybody can afford to live there and participate in person. So doing this by doing things at a distance, finally the technology has caught up, right? This has been a vision many of us have worked on and, many people have had for a long period of time. I do think the technology is now there in terms, not completely, right? Because we still have to worry about the digital divide, but more and more the technology is there in terms of the bandwidth and the computation needed to do it. So I do think that will make a big difference. Thank you.
Thank you.
Okay.
Carla, do you have any final question? Or?
Yes, actually, I saw your slide on the K-12 education, CS education. And how about educating younger children? I mean, K-12 or like, computational thinking, logic, of course, but, preparing those K-12 people.
Right. So I think you said the magic word, computational thinking, right? Because I don't think that for some people programming is the right thing, but I think the deeper skill is the analytic capabilities and the computational thinking point of view. So, that computer science principles course that I was taking. So if you were to search on CSP, Computer Science Principles, AP exam, what you will find are a set of curricula that have been approved by the Advanced Placement Board here in the US, but curricula that was developed with National Science Foundation funding specifically for, in that case, really the high school. But, there's code.org also that's done amazing stuff. If you just go to code.org, if you want to take some of these ideas and use them in middle school, that's sort of where it starts with me, although fun games, like simple graphical programming of have a robot do this thing, kids in the 3rd grade can do that too. So I think there are opportunities. I think we need to think much more broadly than teaching students how to program. I don't think that's the right thing. Well, for some it's the right thing, but I think for the majority of people, it's probably not what you want to do. Okay.
Okay, Jim, thank you very much. It was really insightful. For those attending, we know there were many questions that we couldn't just ask Jim because of the sake of time, but if you can always reach Jim, sending him an email. Jim, thank you very, very much. It was really insightful. I think we are living very difficult times, and it was like a very inspiring talk, touching on very, very important aspects of both research and education in current times. So thank you very much.
Well, again, thank you for the invitation. As I said, I've been down to Brazil many times, and I hope to come down again many times in the future. So I hope I'll get to see some of you in person at some point soon. Thanks again.
Thank you for your inspiring talk. Thank you.
Okay. Bye-bye all.
If you want, I guess you will be available for answering any questions. People might mailing you or
sure.
Like
Also I'll leave it up to you folks if you want to schedule some time where we could get together as a group for a half hour at another time. That would be fine. That would be fine too.
Okay. Thank you very much.
I'll leave it up to you. Okay.
Okay.
Thank you very much, Jen.
Bye-bye, everyone.